last time.
All right.
So we were looking at phi, a Moss form, on gamma naught n, right? And so the fact that it still has a Fourier expansion, x plus iy is a sum. Let's say it's cusp form, and let's say it's even. I'm just making our lives easier. This is an an. Should I keep writing y to the 1/2 k ir, or can I just call this a Whittaker function? Whittaker function of lambda and n of y. Okay. E to the 2 pi I n x. I'll just make it explicit. W lambda n of y is y to the 1/2 k ir being related to lambda as a quarter plus r squared.
This is normalized Bessel function, right? To GLN, like this is generalized.
Right. That's right. Okay, so we have a Fourier expansion. We can make an L function of this thing. LS phi is just you take these coefficients and you put them into a Dirichlet series. If it's a Heck-Moss form, we saw that this will have an Euler product. And last time we showed that it has a functional equation. In analytic continuation, the analytic continuation is that it has an integral representation. So let's actually use that terminology, integral representation, as an integral of phi iy. I guess I want to kill off this y. I would put a y to the -1/2 and a y to the s. In other words, a y to the s -1/2 dy over y integrated from 0 to infinity. That same GL1 geodesic embedded in the GL2 automorphic form. And this thing, we've done this calculation many times, comes out to L of phi s times these gamma factors, gamma 1/2 plus ir, not a half, s plus ir over 2, gamma of s minus ir over 2, and there's some factor of 2 pi to the minus s, something like this. Okay, and then the trick is to define this element, this long element wn, 0, -1, n, 0, which is not in gamma naught n. It's not even in SL2Z, it has determinant n, but it looks like it might be in gamma naught n, because this gamma naught n means that this element, the C element in ABCD, C is divisible by n. But it normalizes. It normalizes gamma naught n, and when we define psi of z to be phi of wn z, this is also invariant under, this is also lives on gamma mod gamma naught n.
And these gammas came from recognizing, right, the Bessel as a convolution.
That's right. These gammas.
Yeah.
Yep. It doesn't really matter for our purposes what they are, actually. We just say Mellin transform of the Whittaker function.
As long as you know, right, this is analytic properties.
That's right. That's right. If we want the analytic continuation, then we had better know that this thing has analytic continuation. Okay. And so when we make that change of variables, y goes to -1 over y, then this becomes the same integral, but with psi and with some factor like n to the, in fact, okay, we're going to get a factor of n to the s minus a half out, or a half minus s. So if we multiply both sides, I'm just reminding you what we did. If we multiply both sides by n to the s over 2, which means I have to multiply here by n to the s over 2, then on the other side, I'll get n to the 1 minus s over 2, and then the completed L function in exactly the same way completed of psi, not at s, but at 1 minus s. Okay, this is the completed L function of phi at s. And this is the completed L function of psi at s. And that's the functional equation. Okay. And in level 1, we could reverse the functional equation. We could reverse the functional equation for L functions to give us the fact that phi itself is automorphic. When n equals 1, I'm just reminding you, when n equals 1, bless you, this L functional equation is enough.
By level, you mean in terms of congruence?
Level means this number n, yeah, gamma naught n. When level n is 1, this L function, this functional equation of the L function is enough to ensure that phi is on H mod, well, gamma not n, but gamma being SL2Z. Okay, so level 1, there's nothing else to do. Wn is an element of SL2Z and it's a generator. We're automatically invariant under translation because we put it into a Fourier series. If we're also invariant under this flip, we're done. Right? Am I going too fast, or do we remember all this? Yeah? Teddy, okay, keep going. But not in higher level. What to do in higher level? What to do? Yes, when n is real. So let's talk about twisting the L function. We need. Conjecturally, we don't need. Conjecturally, the only L functions that exist are the ones that do come from. Well, no, that's not quite right. Yeah, you can cook up things that look like L functions but don't actually. Okay, so yes, we need. It suffices. Let's not say it's a necessary condition, but it suffices.
It's like anything not degenerate enough.
Right. To know about twists. Twist functional equations for twisted L functions. Functional equation of twisted L functions.
So for these degenerate power examples, you wouldn't be able like twisting.
That's right. That's right. Because if you could, then Bayes' converse theorem tells you where they come from. All right, so let's talk about twisting. So let D be coprime to n, and chi a primitive character mod D. Okay, and let's consider. So what I want is somehow to make the L function of phi twisted by chi, which means take the coefficients of phi, multiply by chi, divide by n to the s. Now, really what I want, that's the Fourier looking thing. But if the L function of phi had an Euler product with these factors, Satake parameters, Langland Satake parameters, alpha and beta, it's a degree 2 Euler product. What I really want is to twist the L function is it'll twist each of these factors by chi. So that the product, so it'll twist each of the factors by chi.
This is what you get, right?
So the more general converse theorem, where this is a GL1 cross, GL2 cross GL1, Rankin-Selberg type L function. I'm throwing some terminology. Rankin-Selberg. Although if you're twisting by GL1, you don't usually call it a Rankin-Selberg, you just say twist. But what you will have in general is a GLN cross GLM, Rankin-Selberg L function. And then what you want to do is exactly take the like cross product of all the Satake parameters of one times the other. Should I write that out? You know what I mean?
And this is what Bump does, I suppose, kind of suggestively, even though he doesn't have to.
He does it in several places. He discusses what the Rankin-Selberg L function is. He does the GL2 cross GL2 classically, and I think he talks about GLN cross GLM.
I guess what I'm thinking about is whatever's on chapter 1, right? Where you
Yeah, chapter 1 is the classical. Yeah. So for that, let me call this alpha 1p and alpha 2p. So just a complete aside. If you had a product, a degree D product, J goes from 1 to D, a product of alpha pj, and you had another product, and L of psi s is a product over primes. A product J also goes from 1 to M. I'm running out of letters. 1 minus beta p j over p to the s. then the Rankin-Selberg L function, this is the key. What we want to do is take the product over all P, the product over, let's call this L, not that it matters what our dummy variable is, but it's a product over J going from 1 to D, a product of L going from 1 to M of 1 minus alpha P J beta P L over P to the S. This is the key. This was the key insight that completely unlocked the Langland's philosophy, this Euler product insight, that it's not something in general where you just multiply the coefficients. It's more subtle than that. I mean, you have to define what the coefficients mean in higher rank, but on the level of L functions, it's very easy to say what you're supposed to do. You just take its games on Satake parameters.
So in this baby case that I was talking about, what are the GLs?
Okay, so the baby case, phi is GL2 because it's a degree 2 L function.
You're taking the product of
Chi is GL1, it has a degree 1 L function. And so this Euler product should be a product. So if this guy has Satake parameters alpha P1 and alpha P2, then by this recipe, we should have 1 minus alpha P1 chi of n over P to the S inverse 1 minus alpha P2 2 times chi of P over P to the S inverse. Okay, that's the recipe. And if you multiply this out as a degree 2 thing, what you'll get is a 1 minus alpha P plus alpha P1 plus alpha P2. Yes.
When you have L by cross chi,
Yes.
it's like a tensor, and then down there you use more like just a cross.
Yes, there's not a so there's not often, there's not a uniform way that people notate these things. It's
Are they supposed to be the same?
well, as L functions, they're the same. As thinking about, even here, thinking about what the representations are supposed to be doing, it's also it's also the same.
Are both like a Rankin-Selberg convolution?
They're both Rankin-Selberg, they can both be recognized as Rankin-Selberg convolutions. Now, the way to do this in higher rank is subtle. The way to do it in rank 1 is not subtle at all. You just, if this thing is supposed to be the L function of something, let me take these coefficients and stick them into a Whittaker series, a Fourier expansion, and see what I can learn from that thing. Okay, the only point I want to make here is that alpha P1 plus alpha P2 is AP. So this is where I get this AP chi of P to the S. And then of course there's a secondary term, alpha P1 times alpha P2, which is 1 times chi P, I guess I'm getting here chi P squared. Okay.
niceness from high.
Well, the Euler product, that there's an Euler product is Hecke, and then that it's degree 2 is also Hecke.
Yeah.
And then that I can factor it as just, the quadratic formula. Okay, so if this is the kind of L function we want, and these are its coefficients, then it makes sense to consider what we'll call phi twisted by chi of Z, which is the series an chi of n, this Whittaker function, e to the 2 pi I nx. Because if I take the same Hecke integral, the integral over the vertical geodesic of this thing, we computed that it gives us the L function with whatever the coefficients are, so I'll make those the coefficients. Right? Then, let me just say, then the integral from 0 to infinity of phi chi I y. I guess I always like to multiply by a y to the minus a half here, y to the s, dy over y, will be the completed L function with the gamma factors and the 2 pi to the s of phi times chi at s. Same as before. Okay, so we can get that L function by writing this thing. The question is, does this have any automorphism? We've changed the coefficient. You can't just change the coefficients and expect to have some something still there. Does phi chi have any invariance? We screwed up the coefficients, Karen.
So what's
Who's thinking the division is that we multiply by chi instead of multiplying one time by pi and another time by pi logs.
Yeah, there's a variety of ways of, so there's a variety of L functions. Yeah, you could multiply one by chi bar, and then there'll be a one here. That's another, it's another L function. You know, there's, yeah, like, it's not entirely uniform what people mean by, so some people will put a bar here for the Rankin-Selberg L function, that it should be AP times BP bar. You'll see different definitions in the literature.
So this is just depend on application, which one?
Yeah, depending on what you're trying to accomplish. As you'll see, the theorem that we're going to prove requires knowledge, not requires knowledge, but it suffices to have knowledge. Whoops, did something just, yeah. It suffices to have knowledge on all twists of all primitive characters over all moduli coprime to n. And so, so if you know about twisting this way or twisting with the conjugate, it's just a matter of changing who you're calling chi. Okay, so does this thing have any invariant? Remember, the phi without the chi is invariant under gamma naught n. Phi itself is assumed to be invariant under gamma naught n. Does phi twisted by chi have any invariance? Okay, so let's work out if it does or doesn't. So does that make sense? So we're doing two things. We're going to work out what a twisted L function would be if we had if we started with a Moss form. And then we're going to try to reverse the process. Bayes' converse theorem is reversing the whole process, but first we have to go forwards before we can go backwards.
Right, and so for forward.
This is forward. We're trying to understand, you take this coefficient, you twist it by chi. Does it have an invariance given that gamma naught has an invariance? So that we can apply, so that we can analytically continue this and write out a functional equation for it.
Oh, I see.
Once we have that, then we can guess what a functional equation would have to satisfy. And say, if something satisfies all of these functional equations for all twists, then it must have come from something invariant under gamma naught n.
Right, so we're just pushing forward the process because that's what we did in the other case.
Right. Right, but in the other case, there was nothing to do because we weren't twisting. Now we actually have something to do. Does phi chi have any invariance? I screwed it up. I changed the coefficients. We're assuming. We assumed. Yeah.
So we're not doing a converse yet.
We're not doing a converse yet. In order to build up to the converse, I have to know what functional equation
Okay,
I need to require, so that when I require that of the coefficients, then I can say, to state the converse theorem, I first have to prove,
Need to know the answer and then back.
I need to know the answer back. Exactly. So first we have to work out what the answer is.
Right.
Okay. So it's like a converse theorem. I mean, it's not a converse theorem, but it's like a converse theorem because here's a series that I've cooked up and I don't know that it has invariance.
Right.
And the converse theorem is exactly that, but here it's sort of a pre-converse theorem. Okay. Does it have any invariance? All right. So if I stick in gamma here, well, that's going to change all of this. And what can we say about it? So here's the key idea. The key idea is to go back to the Fourier transform of chi. If you remember chi hat of M, we defined this a long time ago, a sum over n mod d. The discriminant of chi is d. It's primitive. Did I say primitive? I hope I said primitive. Okay, I said primitive. Good. The phi could have some Nebin types. It could have a character on gamma naught n. I'm assuming that Nebin typus is trivial. Never mind if you don't know what that is. But the Nebin typus, Nebin typus. So I'm going to call this trivial Nebin. I'm going to consider trivial Nebin type. But there's, if you read, I think I mean, it costs nothing to add an extra character, except you carry that character around with you everywhere and doesn't contribute to the calculation. So I'm just going to say that it's trivial. So now that we're twisting, I want to know what this is. Let's go back to the Fourier theory. We have chi, which is primitive, which means I can do all of this out. E to the 2 pi I n m over d, and I like to normalize this with a 1 over root d, and then we recover chi itself by taking the same sum m mod d, and of course the only ones that will contribute are those that are co-prime, the only m's and n's that occur, since chi is 0 on numbers that are not co-prime to d. The same normalizing factor 1 over root d, and chi hat of m e to the minus 2 pi I n m over d. Right? This is just finite Fourier theory.
This would be like, some sort of,
Yes, let's recall what happens. If I make a change of variables, if m is not co-prime to d, this is 0. If m is co-prime to d, I make a change of variables, n goes to n m bar. What will come out is a chi of m bar and a Gauss sum. Exactly. Tau of chi, the Gauss sum, and then there's this normalizing factor, 1 over root d. So actually the absolute value of the Fourier transform is 1. Just like the absolute value of chi. Or it could be 0. And when I put that in here, I'm just reminding you these formulas. We've done all this before. So I get a chi, tau of chi over, so I'm putting in this for chi hat. So I get a tau of chi over root d, that's over d, a sum over m mod d co-prime. I get a chi of m bar and an e to the minus 2 pi I n yeah. I need a little more room. Yes, if I can pull that out of the way, I can pull this a little to the left. This, I don't want to lose this. I don't want to write it too small. Okay. So this is e to the, what happened? I lost an I. E to the 2 pi I and m, e to the minus 2 pi I and m over d. And there's a minus sign here. I want to make a change of variables. M goes to minus m and move that minus sign outside for no good reason, just to keep a chi of minus 1 here, so that it looks just like this. Okay, so anyway, if you didn't follow all of that, we had derived this formula for chi, and this is the way that we extended chi to a function on the real numbers. Right now, it's a function of n or complex numbers or whatever you want, p-adic numbers. We have this formula. So I'm going to stick that in for chi here. Tau, yes, I'm sorry, where tau of chi is the Fourier transform at 1. It's a sum over n mod d of chi of n e to the 2 pi I n times 1 over d. So there's only one Fourier transform. All Fourier transforms are just chi of m times the Fourier transform at 1. These are nice, and these have absolute value root d.
Then when they're not primitive, then
That's right. That's right. So I'll stick to primitive character.
and is it in general, do they usually suffice to deal with really primitive characters?
In this application, it will suffice.
Or are there other applications in which you might have to?
No, I don't think there's a good. I don't know of an important converse theorem type application where you need to deal where the twists have to be twists by things that are clashing against the thing that you're twist. Yeah. Usually you want to avoid the bad primes, and you have lots of twists, and you have lots of flexibility within those twists to force all the functional equations that you want.
Okay, that's good to know, right? Because otherwise you'd have to like redevelop this theory, right? To, like, address.
Well, people have developed the theory when D is not coprime to N, just because they want to know, what every place is, not just the good places. If you actually want to define an L function, you want to know that. Here,
No, just the very first one.
this thing, chi of -1.
And it should be either minus 2 pi.
It was e to the minus 2 pi I, and I made a change of variables. M goes to minus m, which is what put out the -1 there.
Okay.
So that this -1 took a little walk to here.
We won't be able to control the evenness of the character.
We don't need to worry about even or oddness of the character.
So just be carrying the kind of negative one.
Yeah, the chi of -1's there. Yeah, we'll carry it around. Okay, so let's put that back into phi. So phi chi of z is a sum of its chi of -1, tau of chi over d, a sum over m mod d coprime, chi. I mean, the coprime you can write or not write, it's up to you because chi is going to kill anything not coprime d anyway. I just always like to have the variables run over the thing they should run over. And then I haven't put in this character, so it's going to be e to the sum of n going from 1 to infinity, an, the Whittaker function of lambda n at y, e to the 2 pi I n x, and an e to the 2 pi I n m over d. Does everyone agree with this?
Okay, at this point, you've,
I've-
at this point, you've already switched.
And I switched the orders. So it used to be e to the 2 pi I n x. So this thing is just phi itself. And then the only thing that doesn't, the chi, the twisting by chi turned into a twisting by the additive character. And the additive character only comes in here with an e to the 2 pi n m over d. I kind of like this. Okay, maybe more books should show you what went where as you're looking for it.
Right, and then it's x plus n over d because you're already summing over the images.
Yeah, that's here. Okay. Now here's the cool observation. I claim that this whole thing, now including this, is phi itself evaluated not at z, but at z. Well, the y hasn't changed at all, but I translate by m over d. And if I how do I want to say this? Deprojectivize this? Is that a word? Watch what happens. What happens to the imaginary part? So what is this? This is dz plus m over d. So it's just z plus m over d. It has the same y as z itself. And it translates the real part, the imaginary part, nothing happens to this. The real part gets translated by m over d. This is just dz plus m over d, also known as z plus m over d. Nothing has happened to the imaginary part. The real part is translated by m over d. Just recognize it. Okay, so this twisted thing, so look at what we have. This twisted thing is actually a finite sum of phis at these, but these matrices aren't in SL2Z. They have determinant d squared. You could divide by determinant, but then, okay, so if you divide by determinant, then I have a 1 m over d 0, 1. And it'll have determinant 1, but it won't have integer coefficient. So you lose one way or the other. Yeah. So I mean, it can't just be a finite sum of phi itself, right? Yeah, something's gone a little haywire here. Okay, so now let's see what happens for gamma equal to ABCD. And I don't know what conditions I need on ABCD. I want to know what invariance I can guarantee for phi. So phi chi at gamma z, let's just work out what that is. So phi chi of anything is this sum, chi of -1, tau of chi over d, finite sum, m mod d, coprime or not, to you, chi of m bar, and then phi of this matrix, dm0d, or 1 m over d 0, 1, if you prefer, and then gamma z.
So this is like a very similar realization to the one of like the conjugating one in sense.
In a sense, yes. Yeah, you mean when the way that we know that psi, where was this psi? this thing. Yes, the fact that psi is also invariant under gamma naught n because this Wn normalizes gamma naught n. It's a similar computation. Yes, we're about to do a similar computation. Okay. I'm going to want to stick in a factor here. Yeah, I want to stick in a factor, and that I want to conjugate by this. So that factor will be the inverse of this. The inverse of this is I flip the two d's and I negate the m and I divide by the determinant. The determinant is d squared. So I'm dividing by d squared. So that's 1 over d, negative m over d squared, 0, 1 over d. And then I stick in, I thought I left myself enough room, but apparently not. D m 0 d z. Okay, so these two matrices together are the identity. Okay, so I want to work out what this thing is.
A minus A.
Yes,
Matrices now.
yes. Okay, so let's work. So there's no substitute for calculation. Oh, maybe there is. Can I do it in Mathematica? This is where it starts getting tedious. Maybe I can do it in Mathematica. The question is, what's faster? Okay. Okay, so I have a matrix. D. Oh, D means derivative. DD. M. 0. D. Times the matrix A, B, C, D. Times the inverse of that matrix. I could just say inverse. Well, let's say what it is explicitly. 1 over D, negative m over D squared, 0, and 1 over D. Okay, let's expand that all out and show it to me as a matrix. Yeah, a little ugly. There we go. Okay, so this whole thing comes out to A plus CM over D. A plus CM over D. Here, yeah, DD because capital D means differentiate. Yeah. B minus, okay, B plus, let's write it like this. B plus M over D times D minus A minus C M squared over D squared minus C M squared over D squared, and then a C here, and then a D minus CM over D. D minus CM over D.
The coefficients of gamma are ABC.
Yes, gamma is ABC. Okay, so we take a, if you're bored, check out that the calculation comes out to what Mathematica says it does.
And here we manipulate the determinant.
We already have kept track of the determinant. I mean, assuming gamma has determinant 1, this thing conjugated also has to have determinant 1, right? The determinant of this thing, here's a check of whether I entered it right. In fact, is a good check. What's the determinant of this? Yeah, AD minus BC.
Oh, I was just wondering if we could like simplify the upright coordinate.
I can't simplify the upper right coordinate. It's not going to get much better, but notice this. If gamma is in gamma naught n, then C is 0 mod n. So that's this C. That's good. Phi is invariant under things that are integer matrices with a 0 here. Problem is these aren't integer matrices unless we make them. What if C is also 0 mod D squared? So now let's assume C is also 0 mod D squared. Then that's a matrix. Then that's an integer. And so is that. And so is that.
This would be like
A different congruence group. Yes. So what if D and A are 1 mod? Also assume, for example, that A and D are both 1 mod D.
I see.
Then this will be an integer. And now this whole thing, if we assume that this gamma came from, what is this? Gamma naught of n d squared intersect, I don't know, intersect gamma 1 of D would be enough. Right? Gamma 1 of D will guarantee that C is 0 mod D. It's already 0 mod D squared, and that A and D are 1 mod D. So this is certainly a congruence group. If gamma is in this congruence group, then this whole thing is in gamma naught n. Does that make sense? But what do we know about gamma naught n and phi? Phi is invariant under gamma naught n. So that means, let's call this a lemma. Let's put it, if you like it, then you should have put a name on it. Lemma. Yes.
So when you say gamma belongs to intersection, we look at gamma belongs to intersection of gamma equal n intersect to gamma equal t squared. Right?
Sure. Yeah. I don't actually care what the congruence group is. I just want to know that there is a congruence group so that this phi with twisted by chi is automorphic with respect to that congruence group. So if gamma is in whatever, it's just some shorthand for the conditions that I want to make sure that this thing is there. Well, it certainly contains gamma of n d squared. This contains the principal congruence group of level n d squared, for example.
So like certainly at least.
So it's certainly congruence. Yeah. I guess I could be lazy and call this gamma 1 of n d squared. Then all the conditions that I need are satisfied. But I don't need it to be, if you're a congruent, I want it to be not, there's, all that matters is that it's some congruence group. Then phi psi of gamma z, well, what do I get? This part all falls out. And what's left is phi of dm0 dz summed over this and summed over that. But that's exactly phi chi itself. Is phi chi of z. Bless you. Does that make sense? So I put in a gamma here. That gamma hits the gamma z with this dm0d out front. But if I stick in this thing here and there, in other words, move it by the conjugate, I get a matrix that under these conditions is in gamma naught n. And phi is invariant under anything in gamma naught n. So this whole thing is gone.
These are things you're multiplying these three matrices on the left.
It doesn't matter if these three left matrices, but these three left matrices become this one big matrix.
Exactly.
And that's in gamma naught n, so they're gone. And now I have phi of dm0d z times chi summed over, and then these constants. That's exactly what phi is at z.
I see, which is what we were doing.
Which is what we were doing.
Earlier.
Yeah.
So
Okay.
You're getting invariance as well, and gamma is this intersection.
All right. What did we do last time? Recall how we got a functional equation. To get a functional equation or functional equation of the L function of phi chi s, which is the L function of phi times chi s. For this functional equation, we made this psi. We used psi of z, which was defined to be phi of wn z. Right? In other words, i.e., phi of z is psi of wn inverse z. right? We stuck in, you remember this element, 0, -1, n 0
I'm still a little hung up on some of the stuff before.
on this lemma?
So what you're saying is if phi is invariant under gamma one,
Yes,
then the twisted, you're getting invariance under gamma zero and d squared intersect.
yes.
You're not saying that you're getting full.
I'm assuming that phi is invariant under gamma naught n, then phi chi is invariant under this group.
So you're not getting, yeah.
I'm not getting invariance under gamma naught n itself.
So that's something we'll have to keep in mind.
That's right. At level 1, in order to get a functional equation, we introduce this psi z, which is phi of WNZ. So let's just reverse that. Phi is psi of Wn inverse z. Right? And let's put that into phi chi. Let's see, do I want a WND squared? Yes. Yes, I do. Okay. So let psi chi of z be phi chi of not Wn, but WND squared. That C element, phi chi is not invariant under gamma naught n. It is invariant under gamma naught ND squared. So I'm going to put here -1, 0, 0, ND squared Z. And I want to know what this has to do. Does this have some invariance?
So you don't have to stick in this ND squared.
Yes. What we did at level 1, what we did before we twisted, it's not level 1, it's level n, but d equals 1. With no twisting, what we did in order to get an L function was relate phi to psi, where psi is phi, with iy sent to I over y times n. Now I'm going to need to send, that was because the C element has to be 0 mod n. Now the C element has to be 0 mod ND squared.
Oh, it's just,
For phi twisted by chi.
you're just saying literally the same thing.
Yes, let's try the same thing.
And then
And let's see if it works.
This is invariant under conjugation.
Well, let's see. Let's see. Okay, so what do we know about this thing? Okay, phi chi of anything is this formula. Chi -1, tau, this stuff. Chi of -1, tau of chi over d, a sum over m coprime to d, chi of m bar, and then phi of, is it d0 md times z? Yes. d m0 d times z, but z is being replaced by this thing, 0, -1, nd squared 0 z. I'm just plugging in the definition, what we worked out for phi chi. Now I want to move from size to size. I have size in terms of phis, but phi is psi of Wn inverse. So let me stick that in. Since there's very little that has to change, I'm going to use the magic of copy and paste. Okay. Instead of phi, I'm just going to put psi of Wn inverse. Phi is psi of Wn inverse. Oh boy. And I'm going to do one other thing, which is I'm going to stick in something here. But what the something is going to be a little complicated. So rather than guess what it's going to be ahead of time, I want something like dm0d, but I don't know that m is going to be the right thing when all of the dust settles. So I'm going to put another variable, L, and I'll put a DL0D.
It's a good thing we have mathematics.
It's a good thing we have Mathematica, which we'll make good use of in just a second. The inverse of this matrix is 1 over D, negative L over D squared, 0, 1 over D. So I can do this for any L. This is the identity for any L. So I haven't done anything.
It's literally.
It's literally the same thing. Okay. And the question is, what is this big fourfold product come out to?
This is why we teach matrix algebra.
This is why we teach matrix multiplication and matrix algebra. Yes, we could do. Should we do the calculation or should we send it to Mathematica? Mathematica. I'm glad you agree. Okay. What can I? It's really not that bad. I mean, people did do these calculations by hand before Mathematica existed. Just there you go. Yeah.
I mean, this clarifies for me, like, why, the first time I read this, I was like so confused as to why is it this huge mess of matrices?
Yes. It's because there's no way to get around. Oh, n is also something, so I have to make it nn. Oh, and I want the inverse here. So the inverse is going to be I flip the diagonals, I negate the off diagonals, and I divide by the determinant. The determinant is n. So actually I get 1 over nn and a negative 1 there. This inverse thing is 0, 1 over n, negative 1, 0. 1, correct.
The key here is just recognizing where does the twisted thing have the invariance at all. That's
Yes.
sort of like- because that is what brings in all these matrices.
That's right.
The first time I saw it, I was like, I didn't see that connection, and I just thought, why are we arbitrarily just sticking a bunch of?
Yeah, it's not arbitrary. It all works out. Yep. Okay, so I have Wn inverse. I have dm0d. It's like dm weapons of, no, there's no W. Oh, there's WMD. That's why. Okay. 0. Oops. 0, negative 1. N d squared 0. That's this matrix. And the last matrix is 1 over D, negative L over D squared, 0 and 1 over D. God, this is going to be pretty awful. Expand.
This is quite the leap of faith that people took when they first did this.
It's pretty natural. Well,
I mean, it's like, it's natural to state it, but is it like, do you actually like really know, like, oh, this matrix stuff will actually,
no, there's all kinds of calculations that you don't know they're going to work out until you do them.
and that's what I think, that's where the leap is. You're doing these nasty.
Yeah.
matrix multiplication, and I mean,
So I know, you know, that they didn't put some down, so people just don't know which one.
I mean, but the first time.
If there's any justice in the world.
I mean, that's what I mean, if there's any justice in the world, somebody did this for the first time before they knew there was justice in the world.
That's right.
We're,
But that's-
of course, we're doing this from the point of view where we already know that it's gonna work out, but.
Well, the section of subgroup defining figures is also.
I mean, I agree the setting is important, but we're mixing settings here, right? Like, we're mixing different matrices here
Yeah.
in a sense. I can see how somebody would write this down and be like, okay, we need to check whether this would work, to see if there's justice in the world.
Yeah. Okay, so when we put those 4 matrices together, 1, 2, 3, 4, we multiply this all out, and this becomes d squared negative dl negative dmn by the looks of it.
It's actually pretty-
And it's not so bad. 1 plus L M N. Okay. Now, wait a second. What's the determinant of this thing? Because psi, remember, psi itself lives on gamma naught n. And I have an n here. So as long as these are all integers and determinant 1,
They're all in.
they're all integers. If the determinant's 1, then this thing is gone. So what's the determinant? What is it? And we have an L to play with. It's going to be d squared. The determinant is d squared. Regardless of L. Yeah. Yeah. You can see it there. Yeah. The determinant is d squared. In fact, the determinant has to be d squared. This thing has determinant 1 over n. This has determinant d squared. This has determinant 1 over d squared. And this has determinant n d squared. So this d squared and that d squared cancel. This n and 1 over n cancel. But there's a d squared left over. Yes. Sometimes it's overkill and you realize. Okay, so in order to get something of determinant 1, I have to divide by d. Because it's a 2 by 2 matrix, that'll drop the determinant by d squared. Okay, so this has the same projective action as the matrix D. I'm dividing everybody by D. Negative L, negative Mn, and 1 plus Lmn over D. Yes. That's exactly what I'm doing.
Otherwise.
So this is not an integer matrix unless, so if L, what do I want from L? 1 plus L, let me just write it. 1 plus Lmn is 0 mod D, i.e. 1, I'll move to the minus sign, to the other side. M is relatively prime to D, so I can put an M bar. N is relatively prime to D, so I can put an N bar.
Yeah, you're dealing with degenerate sort of things, you have to address this issue.
Yes. So this is exactly the guy I want to put here. This, I could have put any L here, but when I put this L here, I get a matrix in. Then if this is true, then this matrix D, negative L, negative Mn, 1 plus Lmn over D is in gamma not n. Pick any representative. If this matrix, if this whole matrix is in gamma not n, then I can cross it all out. Okay, let's put it all back together.
Wait, and then the top part, the C is the big thing. Where are you dividing by D in
Here,
where you have the product of all the matrices?
I have the product of 4 of the matrices and not the last.
Where did you divide by?
From here to here, I divided by D because the matrix is a projective action. The center doesn't do anything.
You just read it.
I can just recognize that this matrix will, in the end, have the same action as this matrix.
Right.
Okay, so I have chi of negative 1, tau of chi over D, a sum over M mod D whole prime, chi of M bar, and here I get psi of DL0D Z by the invariance of psi. This whole thing is gone. But of course, L is this L.
Sorry, what were the conditions on gamma 0 then? Just the bottom left.
Yep.
Is
Yep, that divisible by n.
by n.
Okay, does that make sense?
What did we start with this?
We started all the way at back is psi of chi, which we defined to be phi chi at this W times Z.
Oh, and then we wanted to be able to write that side.
We worked it all, yeah, we worked all the way down to what, so here's what, so psi, we got this sum. Okay, so let me make a change of variables. Let me make exactly this change of variables. L to negative M bar, N bar, mod D. So M, what is M? M is negative L bar, N bar, mod D. So this is the same thing as summing. I have chi of -1, tau chi of D over D, a sum over L mod D. Chi of M is chi of negative L bar N bar, and there was a bar on it. Psi of DL0 D Z. So instead of summing in this summation, I'm going to change from M being the variable that I sum over to L being the variable that I sum over. And then all I have to do is when I see an M, I replace it with a negative L bar N bar. Yeah, because as N is fixed, minus sign is fixed. So, I mean, it's invertible, so it has to be a bijection.
Right.
Okay, which is why it's good to have that prime there. Okay, so far so good. We're almost there. Here's why I like to have that chi of -1 in front. Boom, boom. So what do we get? I get a chi of N bar bar, that's a chi of N. A tau of chi over D, tau of chi over D. A sum over L of D co prime. And a chi of N, no bar. Oh, chi of N came out, I'm sorry. Chi of L, no bar. Psi of DL0D acting on Z. And this whole thing was psi chi of Z.
Wait, L depended on M.
L depended on
Oh,
M,
that's what
and
it
now I
is.
change variables from M summing over M
We
to
kinda
summing over
have
L.
to do that, right? Otherwise you can't deal with this, because you have an L depending on M,
Yes,
how do you sum this?
right. Okay, now let's compare that to the formula for phi tilde. Phi, we had worked this out. Where was it? Right here. Oh, I guess okay, I guess it's sort of here. I grabbed the tool. It's sort of here, but I don't want the gamma and I don't want all this other stuff. I should have had a little aside. Recall. Let's put a little recall here. Yeah. Yeah, go away, go away, go away.
It's still less work than on the left.
I think so, although it's hard to say. Okay, forget about that gamma, forget about that gamma. I can move the Z back over. Okay, that's it. Recall. What did we do? We started with this thing, which was just the series with the coefficients in. We twisted it by chi. And we got this shape. And now what is this? How does this psi compare to the coefficients? Remember, we started with this being the sum over the sum of the coefficients with a chi of N, with this Whittaker function and e to the 2 pi I n x. And we worked out what this is. This we didn't start with the expansion, with the Whittaker, with the Fourier expansion. We just started with its definition as psi chi of W n d squared Z. Right? This was the definition. Whereas here, this was the definition. And we found this, but now we can compare this by using the same formula with psi replaced by chi. We can compare this to the series. So if I abuse notation, and write psi chi of Z also as a sum of B of N, chi of N, W lambda N Y E of NX, that there's coefficients B, yes. Then what is this? Well, I guess I mean, don't make this definition. Okay, maybe that was the mistake. Don't make that definition. Just look at what this thing is. Look at what this thing is. It's this. I'll make the same definition for psi. the twisted psi. Okay, so let me take back the fact that I'm don't let this. Just consider instead of let.
Maybe see that this is the only thing that's positive now.
It's almost, so I'm going to consider this thing. That's what we worked out. We worked out. So that's what we saw, that this psi is this sum, which is almost what the psi sum would be, except it's missing a couple of funny things. It's missing a factor of chi of -1. It has an extra factor of chi of n. Gosh. Can I write it here? Here, I'll put it here. Psi chi of w n n d squared z is equal to this thing. How does this thing compare to what psi chi would be equal to? It's missing a chi of -1. It has the tau of chi, but the chi is the wrong chi. It's actually psi of chi bar, which is maybe not surprising. Psi chi bar of z would have a chi bar here, would have a chi bar here. And then that would have a tau of chi bar, but I don't have a tau of chi bar, I have a tau of chi. So I have an extra tau of chi, and I'm missing a tau of chi bar. I'm missing a chi of -1, and I have an extra chi of n.
So that's something that I would ask you about.
Yes. What's that? Root number, yeah. Okay. Does this make sense so far? So if you just put all this together, I have a tau of chi. This tau should have been a tau of chi bar, because this is a chi, should have been a chi bar, but is a chi. Oh, this I guess is a chi bar. No, this is a chi. This thing almost looks like what it should, except with chi replaced by chi bar, but then that should have been a chi bar. So let's divide out the chi bar and put in the tau bar. That's it. That's it. This is the identity.
Okay, so you generated this again by just computing this and being like, well,
Yes.
this has to convert to something about psi. So this is the correspondence.
Yes. Now let's go back to our integral. The integral of psi chi of y to the s minus a half dy over y, we said was this completed L function of psi twisted by chi at s, with a 2 pi and the gammas. Okay. Now I'll make a change of variables. I'll replace y by 1 over n d squared y. This integral is the same as the integral from 0 to infinity psi chi of I over n d squared y,
Which is the action.
which is exactly the w d squared n z. Yes. The y to the s minus a half turns into a y to the half minus s dy over y. And there's a factor of n d squared to the a half minus s.
Would it be the S minus?
Well, it's this thing is what's going in for y now. This is what's going in for y here. This is what's going in for y here. So I get an nd squared to the half minus s, just like here. But this thing, we just worked out what this thing is. This thing is this at iy. So this whole thing is n d squared to the half minus s times all of this, chi of -1, tau of chi over tau of chi bar, chi of n. And now what's left is an integral from 0 to infinity, psi chi bar of iy. y to the half minus s dy over y. And this is exactly the completed L function of psi twisted not by chi, but by chi bar, not at s, but at 1 minus s.
Well, that other stuff isn't getting in the way.
Nope. It's all absolute value 1, except for this bit, which we can fix in our usual way. So let's make this a theorem. If I take the completed L function of phi twisted by chi of s, and I multiply it by n d squared to the s over 2. If I multiply this side by s over n d squared to the s over 2, this gives me a 1 minus s over 2. This is n d squared to the 1 minus s over 2 times the completed L function of psi twisted by chi bar at 1 minus s. It just works. It just works. Right? And this is if phi is on gamma naught n. If phi is on gamma naught n, and d is coprime to n, and chi is primitive mod d, chi mod d primitive. Then we have this theorem.
So I guess now we know what's right down.
Now we know it's right down. Now we know it's right down. Okay. Now that we know what the twisted functional equation is, if you're invariant under gamma naught n, let's write down Bayes' converse theorem.
I'm gonna ask for all of these.
I'm going to ask for all of these. Let A and B be sequences. Assume there exists a number n such that for all d coprime to n and all primitive characters mod d, the L function L1 of s with a chi is given by an chi of n over n to the s, and the L function of 2 twisted by chi given by bn chi of n over n to the s are entire. They have analytic continuation. They're first of all defined somewhere. I need these to grow no more than polynomial.
Like the ends, define the ends.
Yep. So I have to assume that they grow no faster than polynomial, so these are defined somewhere, and that they have analytic continuation. So have entire analytic continuation.
Scripts.
Yep. I need to be able to pull contours, bounded in vertical strips. Yep. And the following functional equation. Copy and paste. Way. I don't know. For those that are taking notes, it's no fun to copy and paste because you can't do it on paper. That's okay. It takes me so long to copy and paste anyway that maybe you can write the equation faster than I can doodle it. And this is now the completed L function. I don't know what phi is, and I don't know what psi is. This is L1 and L2 completed in the. Do I have to write out what the completions are? You know what the completions are, and these functional equations. That's the assumption. Bayes' converse theorem. If I have any sequences that grow at worst polynomially and some natural number n. Wait, didn't I miss a bunch of stuff here? Didn't I miss a bunch of stuff? What happened to all this stuff?
Yeah.
I missed a bunch of stuff.
Stuff got lost.
Stuff got lost. Okay, let's fix the theorem so that we can fix the, because otherwise, where does n, what role does n play? There's a little dot there for no good reason. There's a chi of minus n, chi of minus n here. And by the way, tau, let me do a little aside. Tau of chi times tau of chi bar is d. Tau has absolute value root d. So tau of 1 over tau of chi is tau of chi over d. So I can write this as tau of chi squared over d. For no good reason. This is what you'll see in the literature. So you don't have tau of chi and tau of chi bar in the same place. I'm just saying 1 over tau of chi bar. If I move this down here, that's tau of chi over d. So 1 over tau of chi bar is tau of chi over d, and there's already a tau of chi. Okay. So, right. So again, the converse theorem. Assume I have some pair of sequences. A's and B's are a pair of sequences. And I have a natural number with the property. And of course, and I have an eigenvalue. And lambda equal to a quarter plus r squared, which is going to come into, that's in the completion. The implicit gamma factor is in the completion. So that for all d co-prime to n, all chi mod d primitive, if I form these L functions, they converge somewhere. They have entire analytic continuation. They're bounded in vertical strips. And we have this pair of functional equations. Now I have to put in the correct factors here. It's easier just to write them, I think. Can someone tell me what they are? Chi of negative n, tau of chi squared over d. Then, that's all the assumption. Then phi of z defined to be the sequence an, the Whittaker function of lambda at y, e of nx, is gamma naught n invariant, i.e. a Moss form, because it's already an eigenfunction of the Laplacian with eigenvalue lambda, but now it's actually a Moss form, i.e. a Moss form.
That's I guess then this sort of tells you, right, that like not that many pairs of sequencers actually give you this function.
Could satisfy all of these conditions. Yes, exactly.
Because otherwise, like then, getting Moss form would be easy.
Yes. And it tells you that these twists are substitutes for knowing group actions. That's the key. That's the key of the converse theorem. You have some automorphic representation. You don't know that it's automorphic. You don't know that it has this invariance. If the L function, the twisted L functions have the right functional equations, that's a substitute for the invariance.
It seems like a line of lead.
It is I mean,
You're going from one functional equation, right? To like
I'm going from infinitely many functional equations. In fact, only finitely many would already be enough, but never mind. Let's.
one of the trivial.
Yes.
You're going from one, and now you're going to like infinitely many.
Well, it's an infinite group. The invariance under gamma naught n. Of course, there are only finitely many generators of gamma naught n.
So that's what you mean by like, oh, technically, as for finitely many.
That's right.
given the
That's
finite
right.
list of generators.
That's right.
We all have to give away and to line.
That's right.
That's very much.
Yeah, it is enough to know this just for those d that are co-prime to n. And as you'll see, there are actually rather few d's that we really need to know this for to be able to conclude this.
Really looking forward to this proof.
Yeah.
It's
Well,
amazing that you can't do it, right, without these infinite analysis somehow,
Yeah. Okay, but with 2 minutes left, I think I should just stop and